Now that we've discussed principal component analysis, we're now going to look at a second technique called tSNE, and that stands for T-distributed stochastic neighbor embedding. Again, it sounds complicated, but the idea is relatively simple. Let's take a look. Okay, tSNE, what is it? It is just like principal component analysis, with the difference is principal component analysis has a linear formula to create principal components. This is a nonlinear version of principal component analysis. Also, with principal component analysis, you get lots of principal components. So if you've got 10 variables, you'll get 10 PCAs. You'll get 10 principal components. You got 10 variable, 10 principal components, and then you kind of whittle it down to like 3, 4, 5, something like that. With tSNE, you only get 2, maybe 3 dimensions. So we're only going to get a couple of those things. If we're going to do this in R, the library that you're going to need to load is this guy right here, R tSNE. And when you get R tSNE, we have to set 2 things. We set the number of dimensions. You can set it to 2 or 3. Usually people set it to 2. The other thing we have to set is a thing called perplexity. Now, what is that? That is a number that essentially is saying, do we care more about local or global aspects of the data? What does that even mean? I don't think anybody can really explain that in good English terms, but here I'll give it my best shot. The value of perplexity would be at least 2, and it can go on to a very large number. But a value of 2, smaller values basically, is it pays more attention to local aspects of the data. In other words, the groupings become more dispersed, more, less tight. And larger values pay more attention to global aspects of the data, and you get tighter groups. We're going to see some examples of that later in another video, and it'll make more sense. But basically, it's going to be a trial and error technique to see what works best. Usually, people set the perplexity value to some number between 5 and 50. Usually, the convention is people start with 30. Why 30? That's just what people start with. And you will have to run it several times because it is there's a random number generator. And so you can run this thing. And unlike principal components, you'll get the same answer every time. You run tSNE and you'll get different answers every time. So you should run it a couple of times to see what works. In R, we have to run a command called unique before we can run R tSNE. The reason why you do that is because tSNE does not like duplicate records. So we're going to use that also. So one of the bad things about the R program, R tSNE, is that there's no predict function. So once we have the answers, you're like, well, what do I do with it? Well, not a lot because there's no predict function. But there's a workaround, and we're going to look at this later. The workaround is we can develop a model to predict our tSNE values after we get them, and we can use linear regression. I don't advise that because this is nonlinear. I recommend, if you're going to do this, to use random forest or gradient boosting or some other more exotic machine learning technique, maybe, but random forests work just fine. And uses for this, we're going to use this for dimension reduction and maybe finding new relationships in the data. This is a popular technique, and it's gaining in popularity because it really finds complex relationships in the data you might not know about. But because it doesn't have, it's not as easy to understand what's going on in the formula. It's not something like principal component analysis. We can look at the principal components and explain what each of these are. this is not as easy to do. So it's not explainable. So anyway, we're going to take a look at tSNE in the next video.